Getting close, huh? Now, that's Idaho Falls, right? Oh, no, no, okay. So where's Idaho Falls? They're not online yet. Okay. They probably, hopefully, they will hear me okay, right? I mean, I guess.
We can hear you in Idaho Falls.
Oh, good, good, great. Wow, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I guess we can get started. Let's look at the, I guess, the PowerPoint first. My name is Arya Ibrahimpur, or Dr. E for short. Okay, since my last name is too hard to pronounce, right? I'm a professor in civil engineering department. Okay, and what I'm going to do today is to talk about bridges in general, or bridge structures in general, and then we can talk about a project that we are going to be doing in the next couple of weeks also. Okay. So let's again talk about this a little bit. Then, of course, I'm going to talk about another program which is put out by West Point. So we'll get to that later after the presentation, or maybe in the middle of it, depending on how it goes. So I guess we can get started. There are some other people coming in. Okay, well, all right. So let's talk about bridges. By the way, what I did last night, I posted this whole presentation on the web. Dr. Sato has a directory on MOSFET, right? Under Sato, ENGR 120, and then you should see that there too. In addition to that, you will see the bridge rules as well later on. So let's talk about bridge uses and types of bridges that exist. Well, bridges are designed for any kind of a vehicle, right? Trains, road traffic, trucks and so on, and as well as pedestrians, as well as, believe it or not, for transportation of water. Okay, so aqueducts are kind of a bridge that will transport water, and they resemble long bridges, like the Roman bridges from long time ago, right? So now, having said that, let's talk about types of bridges. I listed here 6 types of bridges: beam or girder bridges, truss bridges, arch bridges, cantilever, suspension, and cable stayed, which are more of a modern bridges, right? So let's talk about some of these, just to give you some introduction. And now, so for beam or girder bridges, by the way, girder is the same as beam, except typically like deeper beam. And beams are what, like horizontal members, right? Which can typically carry vertical loads. So, so these are, again, pretty simple bridges, as you can see on the left. And maybe I should use my pointer, right? So over here is a, let me close this one, is a typical, log bridge, right, that you can see, maybe in forests and things of this nature, that bridge that goes across a river or a stream. So that's, again, more primitive way of looking at bridges. Now, more modern one, as far as beams or girder bridges, here I'm showing you 2 different ones. One is a steel bridge. At the bottom is the concrete bridge. So here you have a steel I-beam, right, which are typically very deep, right? And here you see a concrete box girder bridge. And by box girder, I mean it sort of looks like a box, right? And of course, with concrete, you have to have reinforcing in it too, right? So that the concrete wouldn't break in tension. Remember that concrete is pretty weak in tension, but pretty strong in compression, right? And then over here, you can see a bridge, which is, again, a concrete, reinforced concrete bridge on the right-hand side. And this was damaged, or actually pretty much failed, right, in the 1994 Northridge earthquake. Okay, so this one should show you what I mean by those rebars, those reinforcing steel rebars. These are beams or girder bridges. And just to show you how the forces act on beam bridges, if you put a load on it, notice that it goes into both tension and compression. Here, the red arrows are supposed to be compression toward the top of the bridge, or the girder, and the tension are at the bottom. Okay. Next one, the truss bridges. These are typically composed of the so-called two-force members. Okay. So, and they're usually connected at their ends, and by some kind of a gusset jointed plates. They're either bolted or riveted or welded. And for all practical purposes, we assume these to be pin connected. By pin, what do I mean by pin connection? I mean, the rotation is possible about the point, right? And maybe I should show it over here so that everybody else can see. So the rotation is possible about the point, but the point is that since you have too many of these members in a truss bridge, of course, you really don't see any rotation, right? But it's easier to analyze it. Why? Because you would see only tension or compression in each one of these members. So for example, if you see this railway bridge here, each one of these members, each one of these truss members will either go in tension or compression, which will make it easier for you to analyze, right? So if you're avoiding any kind of a bending, by bending I mean any kind of action that would look like this. I hope, can they see me if I do this on the Elmo? Okay. So bending, can you superimpose it? Okay. Bend, again, tension is this way, right? Compression is the reverse, and bending is when you bend something, right? Of course, bending introduces tension and compression at the top and the bottom, of course, right? But in trusses, we typically try to avoid bending, just go tension or compression. So your bridge that you're going to be designing would be hopefully a truss bridge, right? I mean, more or less. So again, there are a couple of pictures here. So these are the old railway bridges that we had a long time ago. Nowadays, they don't use truss bridges as much. Here's another picture of truss bridges. You can see either tension or compression in these members. And at the bottom, you can see elements of a truss bridge, okay? This is kind of interesting because you have the roadway typically, or a deck, and then the loads are transferred from the deck to the so-called stringers, which are those green ones, and then to the floor beams, which are those blue lines, right, or those beams. And then from those, it goes to these joints at the bottom of that orange panel, which is your truss, right? So it's a sequence of events that happens for it to get to those joints, and that's how we model them in a computer program or by hand or what have you, okay? So that's, again, a truss bridge. Now, an arch bridge, these are the old bridges, right? These are the ones that are made from masonry or bricks and things of this nature, right? And let me ask you a question. In arch bridges, what kind of forces do you get? Somebody said compression, right? That's true, okay? So arch bridges are by design, are made such that most of the elements will go into compression only. So you're trying to avoid tension, pulling action, right? Or any kind of a bending. And it just happens that, in fact, I talked about this in my structures class, which I'm teaching this semester. In fact, what happens is that if these arches are parabolic shape, okay, and if there's a sort of a uniform load on top of the bridge, like over here, or this bridge here, which is pretty old. This is about, by the way, this bridge on the right-hand side was built in 100 AD. It's almost 2,000 years old, right? It's pretty old bridge, and looks how good it looks too. But anyways, if you put a uniform load on top of the bridge, because of this parabolic action or shape, what happens is that pretty much most of the forces would be in compression, okay? And so that's why you would use what, masonry for these bridges, right? And typically unreinforced masonry, right? Or unreinforced, you know, kind of a brittle material, because everything is in compression, and that's fine. And here you can see what I'm talking about. You see that everything is pretty much red, right? That's all compression. And of course, the forces are taken by the abutment, by the supports here, okay? So these are arch bridges, and so again, these are more of an older style, and nowadays they are not economical to use, especially if you have reinforced concrete and steel, right? There is, you know, no need for these as much. I mean, for aesthetics, they look nice. Here's another kind of a bridge, which is called cantilever bridges. And the name cantilever is sort of misleading because when I talk about or think about cantilever, I'm thinking about the beam. Maybe I can show it over here on the Elmo. I'm thinking about the beam which is fixed on one end and free at the other end, right? That's what you probably know of cantilever, right? So typically in a cantilever beam, again, this is fixed and you put a force over here at the other end for it to bend, right? So now let me go back on the PowerPoint next. So you can see that during the construction, you have a cantilever, which is like fixed at the supports here, and then it's going to span. But then once it's completed, right, you don't really have a free end, right? So, but they call it cantilever anyways. So here you can see this is the so-called cantilever part of the bridge, okay? And because it's sort of fixed over here, and that this is kind of a free, and it's supporting the suspended span. So the cantilever comes from that kind of action. So these are typically longer bridges. It could be composed of steel, typically, or concrete, I guess both, I should say. And they can span longer, all right? Suspension bridges. These are more elegant looking, right? More nicer looking bridges, okay, more modern bridges. These are the older, pedestrian bridges that they still exist. But when I talk about suspension bridges, typically we're looking at more of something like this, right? Like a Golden Gate Bridge, right? Which you typically have a couple of large towers and a main cable, right? And you have also secondary cables which are vertical, and those secondary cables are supporting the bridge deck, right, for traffic, let's say, right? Now notice that these can span pretty long. The longest one that I could find was a bridge in Japan. And this one, it's almost 4 kilometers. You see that? 4 kilometers here in length. And the main span for that bridge, or the longest span, is almost 2 kilometers, okay? So 6,500, over a mile, right, in length. And now by looking at, by comparison, the Golden Gate Bridge, which I'm showing down in here, some information, the Golden Gate Bridge is about 2.7 kilometers in length, but the span between these two towers is about 1.3 kilometers. So it's a little bit less than, of course, yeah, less than this, the longest one. And you can see that this is a long distance, right? So these are typically good across large body of water and so on. Now, here's a picture that shows the forces in cables, the main cable, the secondary cables, the vertical cables, and the towers. Notice that the towers go in compression, right? Does that make sense to you? Because again, the cable is on top of it, sort of pulling the tower down. And one thing that you don't see, by the way, in suspension bridges is that there is a huge amount of concrete at the two ends. Without those amounts of concrete, the bridge cannot, stand up. Does that make sense? Of course, you don't see it. It's under the ground. Okay? So these are actually a pretty expensive part of the bridge. Those huge masses of concrete at the two abutments. Okay? Of course, you have these two, the towers. Now, by contrast, nowadays we have the so-called what? Cable-stayed bridges, right? These are somewhere between cantilever bridges and suspension bridges in length. Okay? Now, this is a bridge in France. This is a pretty recent one in 2004. And I think Dr. Savage showed you some pictures, right? Maybe of this bridge, I think, in his presentation on Monday, was it? Okay. And then this is the one, the Sunshine Skyway Bridge, which is in Florida in 1987. Notice that the span of these bridges, by that I mean between the two towers, are not as long as the suspension bridges, okay? Because it's just not possible. And here, for example, you're looking at what, about 342 meters, right? Which is much less than what we just talked about earlier, right? Over a couple of kilometers, right? I guess a couple of kilometers, or in the case of Golden Gate Bridge was like 1.2 kilometers. So this is like 0.3 kilometers, right? And over here is about 0.37 kilometers for this other bridge, for the Florida bridge. But then again, it's using the same kind of concept. And one nice thing about cable-stayed bridges is that you don't need to have those large abutments anymore. You see that? In suspension bridges, you have to have huge masses at the very end to support those long cables. Here, pretty much all of the forces are carried by the towers. Okay? So that's one added benefit as far as cost is concerned when it comes to cable-stayed bridges. Now let's talk about your project, right? So we talked about these 4 or 6 types of bridges. Let's switch gears to the tools that you could use, right, for your design of bridge. And so what I did, I went on the web and I downloaded this thing called the West Point Bridge Designer. They have, I think, a couple of versions. One of them is 2007 version, which you can download, but they also have 2010, which is not available yet. I think it will come out after February of 2010. So this is the one that we have. And when you go there, I'll show it to you in a minute, you have different options for different kinds of bridges. You know, I guess they're all pretty much truss bridges, of course. But you can have it this form or other form. There's some templates. You can use the template, or you may actually deviate from the template. It's up to you, which is a good thing. So you can play what if kind of a game, right? And so what I did for this bridge here, I went ahead and used the default members. Notice, I don't know if you can see them or not. These members are what? They're all 4.5 meters in length. You see that here? And they're all 160 millimeters in diameter for all of these truss members. Okay, 160 millimeters. All right. So what I did, I ran it under the default, cross-sectional dimensions, right? And on the next page, and I'm saying that, by the way, these members were not good. They failed, and I'll show you what happened. So as you run the truck, in this case, over it, these members buckled, right? Which meant that we had too much what in it? Compression force, right? Pushing action in it. And in this particular software, the red lines represent compression, the blue lines represent tension, okay? And I guess the gray might be somewhere in between. And so then what I did, so again, this bridge under initial member sizes, then what I did, let me go back. How can I go back? Okay, then what I did, I increased these 3 members, just again, by trial and error. I changed them to 180 millimeters for those 3 members. You see that in this box here? And by doing that, of course, this kind of a clever program, it calculates the amount of materials that you're going to be using as far as steel. It gives you a cost estimate on the top. Does that make sense? Okay, so I don't know how accurate it is, but it does give you some values. And of course, by doing that, the cost for me went up, right? By some amount, by some dollar amount. But the good news was that the bridge now could withstand the weight of the truck. Okay, so this is one tool that you have that you guys can use. And like I said, I'm going to come back to it. I guess we have plenty of time. That's one tool. And another tool that you have is this. Actually, in my opinion, kind of a more flexible tool. This is the Johns Hopkins Bridge Designer, okay, by Johns Hopkins University in Maryland, in Baltimore, Maryland. And this one, again, you can you can go to the MOSFET, right? Or you can write it right now if you want. And on MOSFET, once you look at the presentation, you can cut and paste that to the website. And if you do that, you get to here. And it's pretty easy. What you do is this. If I go on the next page, you see just a template in front of you. Not a template, you just see like a grid line in front of you, right? And what you do, you can just, create nodes, like add nodes, right? If you click on it, you can go on anywhere you want. Whoops. Anywhere you want and click to create nodes. So here, how many nodes did I created? 1, 2, 3, 4 nodes. You see that? So those are the joints. Then you can say, all right, I want to add members. So click on this and then click in here and drag it and go to the other one so you have made 1 member, right? And then you can do a few more. And then what did I do next? Oh, then you can say the support. So in here, if you say fixed node, that meant this pin connection. You see that? So fixed means that Horizontally, it cannot move. Vertically, it cannot move either, right? That means fixed in this case, which in my opinion should be really pinned, but that's okay. And horizontal roller is this one here on the right-hand side. So I put it pinned and roller here. Then I put a force in here. So if you add the force and just click in it and just drag it, depending on how much you drag, the force gets larger, right? Kind of a neat, it's a very simple tool. There is no dimension, by the way. So these could be, you can say pound. Whatever you like, you would like it to be, it would be that. So if by putting 100 pound in here, I have what, about 50-pound reaction. That makes sense, right? I mean, there's probably a numerical error here. This should not be 49, this should be 50, right? And then what you do is just click on anywhere on the screen, and it will calculate all of the forces in here. Notice that this force is how much? 80, right? And it's a tension or compression in this member. Compression. And that makes sense, right? The upper chords usually of a truss bridge under gravity load should be what? Should be compression, right? And the lower members in this case should be what? In tension. By the way, the color coding on here is reverse of the other program. The other one, blue, was tension, and so now blue is compression here, so it's kind of confusing. So this is 80, this is 63, and this is what, 100, right? I'm going to show you guys what happens if I just change the height of this bridge from how many units? 1, 2, 3, 4 units to only 2 units over here. You see that? What happened? By changing it from 4 units to only 2 units, this didn't change. That vertical hanger, right, still is 100 pounds. But notice what happens here. This 63 in tension was doubled to 125. Okay, so you can play these what-if games, right, with your bridge, I guess, or whatever you need to do. In fact, this would be a good tool for statics course too. I mean, I'm sure you will be taking it, or you have taken it maybe this semester or something like that. Or maybe you cannot take statics yet, can you? I forget the sequence now. Okay, so you haven't taken that course yet, right? Okay. So once you take statics, you may want to go to this web page. This would be a good tool for you guys to solve some of your problems. Okay, you will thank me later, right? Okay. So notice over here, and then the compression one went from 80 to what? 135. Again, almost doubled up, right? So what's the conclusion here? If I give you a certain height in the bridge rule, make sure that you maximize the height of the bridge to take advantage of that height, right? As much as you can, because that's going to pay off, all right? It will reduce the member forces, and that's what you want, right? So that it wouldn't break. So again, that's the kind of a good tool in my opinion. I just actually came across it a couple of days ago. I didn't know about this one. These are some sources for you guys to take a look at. By the way, this is a bridge in Twin Falls. Pretty nice looking, huh? So it's an arch bridge, arch combined with truss, right? Now, as far as some of the courses that we offer in civil engineering, I just wanted to show you guys where, if you choose to say civil engineering, where in that sequence of courses you would be exposed to structural engineering. After your second year, once you have taken statics and mechanics of materials, you see that? You can take a bunch of courses in different branches of civil engineering, including structures. You take structural analysis, you take steel design, concrete design, and the lab. And then in the last year, you also have some technical elective courses too, right? So you can take, for example, wood design, which is not required, but you can take it as an elective, pre-stressed concrete, composite materials, and advanced mechanics and materials. I brought a book that I use for this semester for my structures class. So this book, again, pretty much talks about the stuff that we just talked about a few minutes ago, all right? And so how you can analyze trusses, arches, cables, and things of this nature. So, so you would, again, having these knowledge, you can do some of those analysis. Also, in our department, there are opportunities for you guys to do undergraduate research if you wish to do so. Okay, but for example, in my area, since my interest is earthquake engineering and structural engineering, I have been able to, in the past, to collaborate with undergraduate students by writing proposals. Typically, the maximum is like $2,000. So, depending on your interest, depending on what is available, some opportunities could exist that you guys can take advantage of. Okay. By the way, I went on sabbatical last semester to University of Nevada in Reno. They have a large laboratory there, and this is a model of a four-span bridge, which is I think about 110 foot in length. So my job was to analyze that under this seismic loading using a computer program. So things of this nature are of interest to me. Another opportunity for you guys would be to be active in the ASCE bridge design competition that we have. So here is another chance that you guys can use some of the knowledge that you gain in the courses, plus some hands-on activity, because now you get to actually not only design it, but also build it in our shop that we have in the engineering. Okay. Typically, freshmen, sophomores get involved also, but maybe not so much in the design, maybe in fabrication and putting things together. But when you become now again junior and senior, once you have some of the other courses, then you have enough information for you guys to be able to really design the bridge and so be more active in it. Okay. There are, I think, about 15 universities in the Pacific Northwest that we compete in. And I think 2 out of those 15 typically go to the nationals. All right? And so if you do really well, you can win those one of those 2 spots, and you can go to the nationals and compete there. So I guess that's pretty much it for me. Any questions so far, by the way? Yes?
Can you go back to second website, the slide for the second website?
Okay, sure. This one? Okay. Again, as I mentioned to you, I have posted this whole presentation on MOSFET, so you guys, if you didn't take notes, are you supposed to write a summary on this? Like a one-page summary, right, or something like that on my presentation? Not for this one? Okay. Darn. My presentation was not good enough, I guess. All right, that's fine. Okay. So let me, before I talk about the bridge rule, let me go in here and tell you how to do, what was that? So once you, should I talk about how to get to that web page for you guys? Do you want me to show you how to get there and where to download stuff from, or you guys can do it on your own, right? Okay, so I guess, so once you go and to that West Point bridge site, which I gave you the web page, right? Again, I'm talking about this one here now, right? So just highlight this, cut and paste it, and you're there. And again, you cannot download the 2010 version. You can only download 2007 version, right? Okay, and that's what I did. And once you download that, I think you get this one here. You see that? Setup 7xexe, right? I think. So then you click on it, and it goes through the setup thing. I guess you guys are better at these things than I am, okay? And then it gives you a whole bunch of other things. And so then once you have that, then you can click on this program, right? And sometimes it gives me error for some reason. I put everything on my jump drive, by the way, so maybe that's why. So I guess I'm going to close that. And so let's just go ahead and just play some game, right? And maybe I can show you what you guys can do. So create a new bridge, fine. And I guess you can read some of these. I haven't done everything, but then it says, are you participating in local bridge design? I guess no. Now here you have, I guess, different length for the bridge deck itself. You can sort of fool around with these, right? By the way, you don't, for your what if kind of a game that you're going to be playing, you don't have to really worry about the length so much, right? It could be anything, basically, right? So because you just want to see, okay, if I have this kind of a structure with these kind of a members, how would it behave, right? That's what you need to worry about, how you can optimize things. And here you can have abutment, you can have like a, let's see, a pier, for example, and the pier, this is the middle column, right, basically. You can have a different height, I suppose, and we don't want to do that because your bridge is going to be freestanding, right? It's going to be between 2 supports. So over here, I think what we're going to do is put 2 tables here, and I think the span is 2 feet. So we will put the bridge there. So there is no support for you guys other than the end supports. So let's go to next. And okay, let's just go with one of these. And notice that you have different options, either none or some of these templates that they have. This is called a Pratt bridge, through bridge. That means that the truss is on top here. The deck means that the road is on top of the truss bridge. And then you have other options. What I did, I think I used this one in my presentation for you guys. I used a deck Warren bridge. And so let's go next. And you can write your name or some ID here. I'm not going to do that. Then I think I'm done. So let me finish this. Then you begin to see your templates, right? Okay. Notice that the nodes at the top, you don't have a choice. These are pretty much fixed. Okay. That's the problem with this program, unless maybe there's other ways. I didn't explore it too much. But to my knowledge, these are fixed. But the bottom one, you can either use these or put them somewhere else, right? But for now, let's just use these nodes, okay? Also keep in mind that as I'm putting information, some things are going to happen on this table too, okay? So let's put nodes. So click on the nodes, and then click, click, and so on. Okay, so these are my new nodes. Again, I didn't have to use these, but I did in this case. Then you can go to do what? Members, right? So then just click between these two nodes and create member. All of these are going to be equilateral triangles, right? The same length, right? And there are, how much are the lengths now? 4.5 meters. You see that in here? So I'm continuing on with this. Okay, that's taking a while now. So I'm going to put some members at the bottom. By the way, if something is wrong, if you don't have enough connections or enough connectivity, I should say, between the joints, then it's going to give you an error message. Okay, so that happened to me a couple of times, so have to be careful. Okay, so here's the bridge. And notice that by default, all of the member sizes are the same, of course, right? And what's the size of the members? These are all bars, meaning like circular bars, right, in cross-section, and diameter is this much. I don't know if you have other choices, but I don't think it matters too much. You can change it. Okay, so you know more about it than I do. Good. So you can do that. So then with this, now let's go ahead and run it, run the truck. So that standard truck is going to be run over the bridge. And if you do that, let's see what happens here. It collapsed, okay? And of course, you can run it slower too if you want to, you know, model slow. Have to go backwards. I guess, yeah, there you go. So you can see maybe, notice that these are red, compression, the blue are tension, and of course, a couple of them buckled for me, right? Or on me, I should say. So what I'm going to do, I'm just going to go back, and notice it tells me that those troublemakers are what, right? So what I'm going to do now, I'm going to press Control and click, 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 members 37, 38, and 39. I'm going to increase the size. See that? So I'm increasing the size to now from 160 went to 170, 180. I guess 180 I tried it and it worked. So now notice that in here, by doing that, those members, so maybe I should come back in here. Where would that be? 30? Yeah, or maybe that's down below, aren't they? Okay, so this member, so what happens if I go back up? Can I see it here? Oh, I should go down more, right? Oh, here we go. I was wondering what happened to them. So these are those members. See that? Okay, so you can see what happened to them. They went to 180 millimeters in diameter, right? So, okay, good. So now let me put this back here, and let's run the bridge again, or the truck again. And it looks like in this case, it was good enough. So again, that's the nice thing about this package. You can do a lot of what if kind of a thing. at least get some kind of idea of what are some of the optimal geometry. Let me do this. Let me erase some of these. You can erase anything you want, right? Maybe I can erase these too. And now what I'm going to do, I'm just going to not use those lower nodes, right? So those lower nodes that I had option, I'm going to change it to something else. So maybe what I should do, maybe, I don't know, I was doing this last night, so maybe I can put one node over here. I'm making it deeper, right? You see that? So maybe one over here. Maybe every other one, I don't know. This probably would be all right. Yeah, something like that. Oops, they don't line up, do they? Let me make them a little bit better lined up. Okay, so let's try again. I guess I can see these lines unless, yeah, so that they would be centered, right? Okay, there you go. So I got them all pretty much lined up, right? And now, I guess I can just do this kind of a thing. So I'm just, playing around with it, right? I mean, it's not exact science, right? At this point. Maybe I can, yeah, that's fine. Okay, maybe I can do, I just maybe can put some of them overlapping. That's okay too, right? I mean, this is overlapping. There is no node here, right, guys? So I can maybe overlap these two if I want, or these two, or so. I mean, you can add and subtract whatever you like, and maybe I should put something at the bottom too, right? Okay, so let's see what happens to member sizes. I don't know if it chose things. Notice some of them are 180, some of them are 160. So some of them are probably chosen by default, and if you don't like them, you can change them on your own later, right? By doing these things. So now let's run the bridge, run the truck. Oh, okay. Looks like it was all right. But notice that those red ones are being compressed a lot, aren't they? Okay. And notice that, did you see the deflection between this one and the previous one? This one didn't deform very much down, right? Why? Because it's so stiff. Does that make sense? So because I'm using more of a height. So the deeper a bridge is, the better it is, right? It can withstand more load. So just remember that. Okay. And so let me just go back for the heck of it here. Let me just maybe select, was it this one here that was a red one? Why don't I just do this for the sake of just seeing what happens? They were 180, right? No, actually, yeah, let's do two things. Let's just decrease these, but then I'm going to come down and decrease the tension once to just see what happens there. I'm going to do two things. To decrease these, 180, let's just do 160. Now they're longer too, right? So, all right, see what happens. I hope they will buckle now, right? I did, almost. Did it stop? So it might have buckled too much, right? Okay, so it didn't collapse completely, but probably enough. So let me go back. So let's just do a little bit more. I want to see it fail. That's not good, huh? Or go faster maybe, huh? Okay. Okay, I guess it doesn't. The truck driver is pretty smart, right? Okay. So let's maybe do this thing here. So let's just click in here and here. And I want to decrease these, right? I just want to see what happens. It goes. But I'm going to increase these. Oops. Increase these. Okay. So, it's still okay. How about that? Okay. All right. Okay, so much for my idea, huh? So let's do a little bit less. So now I'm up to 100 millimeters, okay? Maybe even less. Let's just break it. Ah, you see that? It's ripped apart, right? That's good. I should have had this picture too. Hopefully something like this wouldn't happen to you guys too much, right? When you're doing your bridge testing. Question? Yeah, Dr. Sato told me that you're going to be using the same group that you used before. Did you have, yeah, some groups, right, before, or some teams, right? And how many did you have in each team? Do you remember? 3? Ooh, 3 may not be enough because that will take us forever to break those bridges. So maybe I'll talk to Dr. Sato and maybe he can talk to you next time, okay? At this point in time, I don't know about the teams. But so let's switch gear and talk about your bridge, okay? Or your bridge rules, I guess. So let's switch to the Elmo, to the overhead. Now I put this, we put this on the web for you, okay? This bridge rules. And what, can you see okay? Maybe zoom on it a little bit more. Can you zoom on it a little bit more, or do I have to do it? I don't know how to zoom. Is this it? No. I don't use these classes. That's my problem. You can't see very well, right? I mean, I can see over here, but you cannot see on the screen.
Maybe you could open it on Moodle and we could see it through the computer.
On MOSFET, that might be a good idea. Somebody had a good idea there. There you go. But I think he's trying to figure it out too. Maybe we can do it at the same time. All right, go in here. What's the address for MOSFET? Okay, that's it. So this is how you guys can go into MOSFET, right? So MOSFET ISU. Well, I'm going to show this to you anyway. So you go to, oh, you cannot see this now. All right. Can you switch back to the screen real quick? Okay, sorry. So you just type in again mosfet.isu.edu. You go in there, and at the bottom toward the end, it should say Sato. See that? And in here should say Engr 120, and this is the rules, okay? I think what happened was that when Dr. Sato put the rules on last night, one of the pictures got screwed up, so maybe I should not use this one, okay? I'm going to bring that to his attention. This picture here, notice that these are supposed to be hooks, so this should have been really down in here, right? So that thing got screwed up, so this should have been, I don't know if I can move it, but this should be, there should be a hook here, right? Okay, that's a hook, and that's supposed to be hook. I'll show it to you over here. So let's just switch back to this if you don't mind. Too complicated, I know. Okay, so this is the rules. By the way, the rules were put together by Dr. Savage, right? So we have a lot of collaborations here, right? So it says maximum group size is 4 people. So in each group, I suppose, right? Only 1 entry per group. The bridge is to be built from spaghetti and glue, okay? And spaghetti shape must be long and thin. Lasagna noodles are not allowed, right? So, so circular ones, those are typical spaghetti noodles, right? So I wouldn't go too crazy on various, just use the standard one. I mean, that's my suggestion, so, but up to you. And then glue can be any kind, right? I think he had in mind like Elmer's glue, but then of course it has to dry up, right? And you would lose some weight of the water, right, in the glue. And I think there is some information about the total weight toward the end. So that is the glue and the noodles, right? I mean the spaghetti and the the glue. The bridge is going to look like this. Okay, so we're going to be putting like 2 tables over here, right? And then we're going to make sure that there is a distance of 2 feet between the 2 edges. Okay. So then, of course, your bridge should be a little bit more than 2 feet, right? Okay, so don't take a chance, right? If it's 2 feet exact, it's going to fall through, right? So this should be a little bit more than 2 feet. And these are the information. So it says the bridge shall be no more than 1.5 foot in height. Okay, so you have some height limitation here, right? And so you have the span and the height measured vertically from the lowest point to the highest point. And the bridge shall have a clear opening passing through the bridge end to end to allow a placement of a loading deck. The following conditions shall be met. Can you see okay? The clear opening from end to end shall allow a 3-inch by 3-inch high block. So I guess we can bring a block, right, which is like 3 inches by 3 inches, and that should go across the bridge, right, like a truck or something, right? So that there should be enough opening for that block to pass through. And support for the deck, the loading deck will consist of a piece of plywood, which I'm going to show you on the next page. It's 1/2 inch in thickness, it's 3 inches in width, and it's 8 inches in length. So imagine the loading is going to be applied through a plywood, right, which is again 8 inches by 3 inches, should be right in the middle of the bridge. There would be 2 hooks at the bottom of the plywood, so you have to slide the plywood inside. If you have, again, enough opening, it should fit, right? And then the hooks, just again, make sure that the hooks there's room for the hooks to go through the bottom of your bridge, right? There should be enough holes in there, right? Otherwise, the hooks will not go through. And then we're going to maybe attach a rope or something to the hooks, and then attach a bucket at the bottom, okay? It will be like a 5-gallon bucket. It wouldn't be too heavy, the bucket itself, maybe couple of pounds or something like that. So maybe if you have a 5-gallon bucket at home, just measure that, right, how much weight that is. So at the minimum, it should handle that, right? And the weight of the plywood and the stuff. So in fact, I can show it to you over here. Here's that 8 inches in length of the plywood. That's again 1/2 inch, and the 2 hooks. So you have to go to the hardware store and get a couple of hooks, and so again come up with this whole thing. And so that has to again slide through, and then we can attach a couple of things in here, and then the bucket will come at the bottom, right? And then what you need to do is we're going to probably give you a scoop or something, and maybe slowly put some kind of, I think we're going to go with sand, all right? So don't put it too fast and not too slow either. Question? No, we are going to do it ourselves. We're going to bring one, okay? And we're going to use the same one for everybody, all right? So yeah, we will do that. And okay, what else? The clear opening should be planned for the hooks to pass through the deck. So that makes sense. The loading deck will be placed in the middle of the bridge, okay? And of course, the middle typically is the worst place to put it, right? Okay. And the final bridge weight shall not exceed 19 ounces, which is 1 pound and 3 ounces. I think he had in mind, if you buy a 1 pound of spaghetti, right? Then I guess he's figuring out maybe 3 ounces at the most of the weight of the glue, right? After it dries up. So and then incremental load will be applied to the loading platform via the hook. Sorry, failure is defined when the bridge breaks or the structure twists. Maybe if it's twisting too much and it's cannot handle the loading, then we will call it failure. Okay. So that's your bridge. Again, this should be on the web. Take a look at it, and I guess that's pretty much it, right? Any questions? The question was that can we use different kind of a pasta or one kind only? I guess the rule doesn't say that, does it? So I would imagine you can use anything you want, right? You can use 2 different kinds, right? Sure, that's fine. That's even probably better.
Professor E.
Other question.
Yeah,
Maybe
we're
you wanna
building.
Push the button, or are you supposed to push the button?
My
yourself?
button's pushed.
Okay.
We're building these outside of class and then coming and bringing them in the day that we're
Yes, yes.
on the 9th.
So I think you can do it outside of the class, right? So plan ahead and again work in teams. So Monday, Dr. Sato will let you know exactly who the team members are, who the groups are, okay? One thing. And then I think next Monday and next Wednesday, you don't have to worry about the bridge. So maybe that week you can work on it, right? And I believe the following week, the following Monday and Wednesday, we will break the bridges. I don't know about that. You might want to ask Dr. Sato. Okay. All right. Well, you have a good day.